new baby. I posted about their neglect on that bed, but this grandparents threatened his inheritance.
I think we're nearly there, folks. Take a look. Yeah, I guess we can get started. Welcome back, everyone. We have a pretty strong class for going into spring break, so that's pretty awesome. These are the hardest ones to attend, I think. For today's class, we're going to be looking into section 3.7. I indicated that the due date is March 27th. That would be meaning we complete it today, so it'd be due across a break. But I'm not going to try to race through this one. If we need to take additional time after the break to finish it up, we will take that time. And so the due date would potentially be 1st of April. That's no joke. It would really be that day if we finish it when we come back. So, well, we have our exam 2 that we went through on the Monday's class. For the people who took the exam in person, I was able to grade those. The results are now available in Moodle, and I have the hard copies. Well, people in class already know that I'm thinking. But for folks who took it at the testing center at Pocatello, I'm still waiting for them to scan the exams and send them to me. That should happen on Friday. And once I get them, I'll begin grading. And once I have them all graded, I'll email you to let you know that your grades are available in the Moodle system. I'll also be able to email your exams back since I'll be getting them digitally. Well, aside from that, we're going to be going for section 3.7, which depends heavily on information from college algebra logarithms. So I'll be looking at that document as well. And going into the next week, we'll have no new quiz, only because of the upcoming spring break. Well, any questions at all, folks, before we get started? Okay, well, it's the last section of chapter 3. The main takeaway of chapter 3 is we defined the derivative, and we just looked at other methods for calculating more and more derivatives for different functions as we saw them. And this is the last class of functions we haven't really got into, the logarithms. So let's take a look. And here's our methods. It looks like a lot of just more calculus-y kind of stuff like you'd expect. But when you look at these functions, they don't really exist in isolation, these formulas rather. It's good to kind of break these up in this sort of way and put down a couple analogies about things we do know about when it comes to differentiation. When we look at a function like natural log x, it's inverse to a second kind of function, y equals e to the x. Actually, calculating this one uses a method called implicit differentiation, but it also relies on the fact that we knew the derivative of this one, its inverse function. So over here on the right, the derivative would be dy dx equals e to the x. So that's if we have the exponential function. If it's a logarithm, that's kind of a nice derivative too, just not as nice as the e to the x function. When you differentiate natural log x, all that happens is you get a 1 over x. So that's a really interesting formula in its own right. And for a quick example, if you had, well, it's hard to write a really quick example, but let's do it anyways. If you had y equals, say, natural log of x squared, let's maybe not do that one. Sorry, let's do 2 natural log x. We'll look at those other ones in a moment. And differentiating this one is going to involve the constant multiple rule, since 2 is multiplying. And you would say just briefly, y prime equals 2 divided by x. Really, I did a couple things. The derivative of the natural log is a 1 over x, but because 2 is multiplying, the 2 just stays in the numerator, and x goes down below. So pretty much that's the punchline. When you differentiate natural log x, you're just setting x down to the denominator. Any questions, folks, with that formula? Okay, this is the reason why people call this, well, the French call it the logarithm naturel. That's why it's ln. We call it the natural logarithm because that's kind of a natural process. And its associated function over here, the exponential, well, it's a pretty natural process as well. It's the only function that simplifies in this nice, clean way. But as soon as you get away from base e, whether in natural log x, which, by the way, just as a reminder, natural log x does mean log base e of x. If you change the base from e to something else, calculus gets a little bit harder. We already knew that from this example. you change from y equals e to the x to this function, y equals, let's say it's 7 to the power of x, that's suddenly a much tougher derivative to deal with because, well, the whole formula has changed. The formula now goes dy dx equals 7 to the power of x multiplied by the natural log of the base, which was 7. So now for these kinds of functions, if your base is not e, you have to pay attention to the actual base because we multiply by the natural log of whatever it happened to be. The same idea over here. If the base is b in this location, well, you almost do the same derivative as before, but you have to do this modification and multiply by natural log b down below. So for a really fast example on this one, let's suppose we had y equals, let's make it just log of 7 times x. So log base 7 times of x is the best way to say that. Let me try all over again on this one. This is the logarithm to the base of 7 of x. There's no times in there. Now, if you differentiate that, y prime would be 1 over x. That's what we would like it to be, just like this formula over here. But once you see that there's a different base, you multiply by that base in the denominator. That's what's being indicated right here as well. Well, those are the two examples and thoughts to keep in mind. And even though I'm going to delete this in the moment, you truly want to keep these two examples together because you're sometimes differentiating when the bases are different. It could be a logarithm or an exponential function. And you definitely want to keep these two examples together. This is when it's an exponential or when it's the associated logarithm to the same base. Well, any last questions, folks, about those two new definitions or two new formulas? Okay, so this got kind of busy, so let's just put a little bracket here to show that one and that one are the new formulas. But it's always good to keep these in context. These are not in isolation. They exist with the other formulas we were dealing with. With that out of the way, let's practice it right away with these two formulas. Over on the left, we have cube root of natural log x. On the right, we have natural log of the cube root of x. That feels the same in a certain sense, but these are totally different functions. Really, the thing that we have to think about once we deal with logarithms are, what are their properties? Because if we don't use the properties of logarithms, some of these derivatives get just needlessly hard. The homework doesn't have to be so terrible, and neither do these as exam questions. So before we get too far away on these, here's the document you definitely will want to take a look at, especially if it's been a while since you've worked with logarithms. I put a bunch of stuff on here about how they're defined, domains and ranges, other interesting properties. But this is probably where you probably want to settle on. The properties of logarithms are what we need to do calculus effectively. So we'll work with this right here and just move it along the document as we go through the problems. Already, we need it for these problems. Well, one of the two. On the first one, for f of x, I would definitely reformat that if we're about to differentiate it. Radical format or radical notation like that is just not very effective to see how our formulas work. So we would want to take our f of x and write it in as natural log x to the power of 1/3. Now that's a little bit easier to deal with. It's still not nice. That's a chain rule problem, and we can't do anything about it. But what you can do something about is this one. Let's redo the same idea. G of x equals the natural logarithm. Let's put in an extra parenthesis, because that cube root of x can be, I guess I don't need extra parenthesis. Not sure why I thought that. Just a big parenthesis. It's x to the power of 1/3. So that power 1/3 is really special. When you see that, and if it's inside a logarithm function, the property we want to use is property number 7. The property number 7, what happens is a power that's here on x can turn into a coefficient. So you can differentiate this one with the chain rule. It works, it's just fine. You have to simplify a little bit more, or you could just simply do this. simplify your function, write it in as g to the x equals 1/3 times the natural log of x. And now that function right here is not too much different than this example. Only difference is 2 versus 1/3 that we have in front. So we escaped the chain rule, and that's always a good idea. Try to use as less formulas from calculus as possible by using properties of logarithms, and that's the theme of all of these problems. Well, maybe not every single one of them, but a majority of them. Let's do the g of x function. That one is a little bit easier to work through. If we're differentiating that, we would say g prime of x equals, first the constant is multiplying, so it stays right where it is, 1/3. We take the derivative of natural log x, it just becomes a 1/x. Let's scroll up to just observe. That's all that's going to happen. Well, it's done, but we should simplify it. It becomes 1/3x, and that would be the official answer for this example here. Well, we did it, folks. That's our first honest derivative for example 1. Any questions at all? I'm running through that one. Okay, observe if we didn't use properties of logarithms right here, let's put a paper trail. Let's call this property number 7. Let me define that because that's shorthand. I'll put down these property numbers to show where we grab these things from properties of logarithms. But now on this one, there is no property to help us with this. The whole function natural log x is raised to the power of 1/3, and so it's a chain rule. There's no getting out of it. But we've done chain rules like these. This is the outer function, which we handle first. And this one is the inner function, which we differentiate second. Can move this down. We have no cost to use properties of logarithms. And let's take a look at the formula above as we work. Differentiating f is going to go like this. F prime of x will be equal to, first the 1/3 will come down. It's now a coefficient. We subtract 3/3, minusing 1 from the numerator, so it's now -2/3. Then we multiply by a derivative. And that's the setup with chain rule. We just handled the outer derivative, derivative number 1. Now for the inner portion, it's just simply natural log x, so it'll go right here. And it's done in that position. Then finally, when it goes here, natural log x, that's when we're using the formula up above. That whole thing, natural log x prime, is just a glorified 1/x in that location. So this turns into 1/3 natural log x to the power of -2/3 times 1/x. We should simplify that, but nothing too major. Some people put this negative exponent down into the denominator. I would say that's a stylistic choice. You can leave it in that position in the numerator if you'd like. The only thing I would do is just multiply across numerators and denominators. This turns into natural log x, power -2/3, divide by 3 times x. Taking that 3 and the x, combining them. Didn't do anything too major. This was most of the way there. Well, those are two very similar functions, and we've seen these kind of analogies before. These kind of examples, we always want to try to train our eyes to see the difference between what the function notation is saying here versus over here, because it's really extremely subtle. And the bigger takeaway is properties of logarithms are what made this one an easier one to get through. Well, we did, folks. That's several derivatives already. Any questions so far? Okay, so these are problems where properties of logarithms work great, like in g of x. But here's a problem where properties of logarithms, well, it doesn't do much for us. And it's kind of a shame, because if properties of logarithms worked right here in part A, that would be fantastic. But algebra involving pluses and minuses is always a little bit more tricky. It's a reason you can't simplify 25 plus 1. You really have to add the 1 together. Now you're stuck with root 26. Same issue here with logarithms. Pluses and minuses, there's nothing in here that works for us. Those pluses and minuses don't count because those are two separate logarithms being added or subtracted. Whereas this is just one logarithm. But still, it's not too bad. Let's write down our formula. D by dx, the derivative with respect to x of natural log x, is simply 1 over x. Now this one's a chain rule, but it's a chain rule a little bit different than what we've seen before. A chain rule is going to have this natural log x as its outer function. And now all of this, the degree 7 polynomial, that one's going to be the inner function. So this is another opportunity to take a look at the chain rule and practice it a little bit more. When we go to differentiate y, it'll become dy dx equals, in our organization, it indicated we're first dealing with natural log x, so we would look at that definition. It's a 1 over x. And so the way you'd probably write it in the chain rule when you're learning it for logarithms is about like this, 1 over something. I kind of copied the definition, but for x, we just put a placeholder. Because it's a chain rule, we multiply by a derivative right away. So that was handling the outer derivative. It looks funky. It's the fraction 1 over x multiplied by something else. Then we take all of this stuff and plug it in. Down in the denominator, we'll see parentheses weren't necessary. It's more of just following a pattern. So you might not do that on every single problem. It's 9x power 7 minus x power 6 plus 5x minus 11. And another thing to observe, every time we've done chain rule, we've always multiplied by the derivative, where 9x7 minus x power 6 plus 5x minus 11 would go once again. But observe, when you simplify these things, that multiplication is just going to throw something up into the numerator. So the way people actually calculate these, once you've done it a lot, is you just take that, copy it down, up in the numerator, you just differentiate what the input was and write it in right exactly there. That's the shorthand. But if you write it out this way, this is the process that gets you there. So this is the way you usually learn it. And then you start taking a little bit more liberties and shortcuts, that kind of stuff. Any questions at all, folks, on this first step starting out? Okay, observe that it was fundamentally just deciding which function went inside the other function in the function composition. So chain rule is all about understanding function composition to begin with. And at this stage, the last thing to do is just work out that derivative. We'll say it's equal to, and now I'm just going to copy this denominator. We're done with it, so we can, not doing anything to it, so we can drop the color coding. I am differentiating this one, so I'll keep the color coding in green to show the change. But I'm just going to multiply into the numerator times 1 and just write in the result here. Going left to right, using power rule a bunch of times, we'll get 63 x power 6. Next one is negative 6 x power 5. This one will turn into just a plus 5. And the constant of negative 11 will vanish. And so now we did it, folks. That's our end derivative. Nothing simplifies on this because of, again, pluses and minuses. If it has a chance to simplify, you would have to factor the numerator and denominator. But the powers are like 6. I would say don't even worry about that. These problems are designed to just be done and right at this step. We're not going to try to factor huge high-degree polynomials. Well, this one is, the first one you're going to see as a typical WebAssign kind of problem. It'd be a typical exam problem as well for the third exam. And from then on out, there's no properties of logarithms for this one, but for everything else, be very suspicious. You can work hard on the chain rule. I mean, that's a valiant effort. But sometimes it's not worth all the time and effort. Here, it's a chain rule problem, but that one simplifies massively. The reason it simplifies is you could rewrite this as f of x equals log to the base of e. That's what the natural log is referring to. The input to that function is e to the x. And that's property number 1 right here. That implies an immediate cancellation as long as your base for the logarithm identifies and exactly matches the base of the exponential. They are inverse functions now, and inverse functions do that sort of cancellation. It just equals x. In fact, we've done this before in the prior sections. We took the natural logs of both sides and showed we get these sort of cancellations. Here, we're just faced with wanting to do that right away, not for equation solving, but more just to avoid the chain rule. So this is how you probably want to start off this one. F of x equals x. And that's nice. This is property number 1 from logarithms. That means the derivative of this thing, f prime of x, is 1. If you carefully did this one with the chain rule, you'll get the same result. You would just get e to the x divided by e to the x. It would cancel and give you a 1. But that's a whole bunch of additional steps. Working out the properties of logarithms is more of a stable operation if you're not taking so many extra steps. But we did it, folks. Part B was really just differentiating x. We just had to recognize that's what it simplifies to. Any questions on getting through that one? Okay, let's try out another one next. Here's where it starts to get not too bad. And part D is where it starts to get pretty terrible. So let's work our way towards that. So first issue on part C is you definitely have noticed that radical notation causes lots of issues with calculus, but also causes issues with properties of logarithms. We want to use property number 7 on this problem. But to use it well, we have to say exactly what that exponent is, and it's not 3. It'd really be 1/3. So this problem should start off by writing out that h of x is 15x times log base 7. Now this one needs a big parenthesis, and then x minus 8 to power 1/3. So this helps us out a lot because if you spotted the issues with this function, we have 15x, which is one function, multiplying log base 7 of another function of x. This is a product rule right here. But you're combining now product rule with chain rule if you don't do anything to that function. But chain rule gets simplified if we move that exponent. So we'll take that whole thing and multiply it here. And this will be property number 7 of logarithms. That one little change makes our life a lot easier. We'll get through the problem much faster. So here's our next step. H of x equals 1/3 times 15x log base 7 of just x minus 8 now. The exponent is gone at that step. Now there's a slight simplification. We might as well take it. H of x next is 5x multiplying log base 7 x minus 8. So all of this is h of x. We have done no work calculus-wise, but in a real sense, it's indirect calculus work because we're just lining up our function to differentiate efficiently. So now we have a product going 5x multiplying log base 7 of x minus 8. And so here's how the product rule should go on this one. First thing we do is we differentiate that 5x. And let me know how this feels as a shortcut. Usually I would write out the 5x with a prime on it, but that's more when we're learning the product rule. If you already know you're differentiating 5x, you'd often just write down a 5, and then that portion's done. We'd multiply by this function, just copying it in. Log base 7, x minus 8. If you have a plus here, or excuse me, if you have a multiplication here, that converts to plus. And you know, that's a common theme. There's a multiplication here, and it converts to plus as well. Division here converts to minus, much like with quotient rule, you have a minus between things. So that's a nice pattern to have. Let's highlight it just to emphasize. Now the next step, I'm copying the 5x, so here it goes. And next, we're multiplying by the derivative of log base 7 of x minus 8. I mentioned we got out of the chain rule on this one, but you have to ask yourself, did we truly really? Sort of. This is a more complicated chain rule because that would have been function 1, function 2, function 3. That's a hard way to analyze. We typically try not to do a chain rule in that process when there's more than one function in the composition. But the moment we move that 1/3, it's still a chain rule where this is the outer function, and that's the inner function. But it's going to be feel a little bit silly when we analyze this and really use the chain rule because the derivative of the inner function is just a 1. It means there's no change in the chain rule, but it's still a good idea to analyze and look at it very critically because if that was a 2x, and we'll see that in our next problems, the chain rule really did matter. And if we didn't see it, we could lose the whole problem. We're about there. Let's first put down our formula. The derivative with respect to x of log base b of x, that's our nastier version, becomes 1 over x, multiplying the natural log of b. So b in our problem is going to be the 7. With all that said and done, I think we're ready to calculate. So first we do the derivative of the outer function. It's a log to the base of 7, so it looks like this. 1 over a placeholder times the natural log of b, which is 7 in this problem. Then because it's a chain rule, we'll multiply by a new derivative going like that. So that's how the chain rule starts with a logarithm. It just looks a little bit weirder because of the natural log 7 there coming from the formula. Next thing to do is take x minus 8. It'll go here and here. And we're finally ready to just finish off the whole derivative. I think the portion in green is the trickiest part of this whole thing, though. Any last questions, folks, about how we got from here to here? Not last questions, you can ask later on, but any questions at the moment? Okay, well, let's finish this off. There's just one last derivative to get through, so I'm mostly copying at this stage. This is 5 log base 7 of x minus 8. Then over here, I'm going to take this 5x, move it into the numerator. The derivative here is just a 1 multiplying 5x, so it'll stay as a 5x. And we'll write plus 5x divided by x minus 8 times natural logarithm of 7. For these problems, it is not expected that you'll add these up. So once you get a bunch of terms adding and subtracting, this is all you have to do. Look for small cancellations like multiplying 5x into the numerator, maybe canceling numerator to denominator if you get the opportunity. But this is where the problems would typically end. Any questions at all, folks, on running through this one? Okay, I put this problem on the notes because there is one like this on WebAssign. And it's tricky. I get a lot of questions on this type of problem specifically because, I mean, there's a lot going on. There's product rule, chain rule, and the derivative is non-standard. So when you see one like this one, this is a good set of notes to come back to and hit the Ask My Teacher button as well if this doesn't help out. I'll be happy to discuss it. So that's a couple tricky derivatives down. Before we take on the next one, it's nasty. I figure let's do a warm-up problem just to see how these kinds of things ought to go. So this is a problem we're inventing right in the middle of the notes. Let's call this a warm-up. So one of the reasons properties of logarithms are looked at very carefully in a college algebra class is it's really vital in calculus just out of nowhere. In calculus, we need to do the following. Expand the given expression. It could be something like the one you saw down below, but let's invent our own. Let's let it be y equals log base 10 of, how about x cubed times y squared divided by let's see, how about nothing too crazy? Z plus 7 to the power of 12. So this would be a typical problem that we'd have to deal with, and it's got all sorts of issues. In its current format, some people call it simplified because it's written in just one spot as compactly as possible. But the word simplify is extremely context sensitive. This is not simplified for the purpose of differentiation. If we want to differentiate that thing, its simplified version is its fully expanded version, where we have to use properties of logarithms to work through. The key ones we usually work with if we're expanding an expression are 5, 6, and 7. And here's how it goes. We typically don't want to take a ton of steps either because we need to do calculus on this thing, so we don't want like 6 steps just on the algebra. So shortcuts are encouraged. Here's how we would probably work through this one. I'd write y equals log base 10, and first, we're using property number 5 to start. Only reason is we have a multiplication right here, whether it's multiplication bullets right there or not, we're implying multiplication. So I'll begin with log base 10 of x cubed plus log base 10 of y squared. And that handles the numerator with that formula there, adding things together. The next thing we do is observe you have a denominator. That means we're using property number 6 next. The moment you see a fraction sign and you're dividing by something, this will turn into minus log base 10 of z plus 7 to the power of 12, which means I need additional parentheses to properly convey it's just z plus 7 to that 12th power, not the whole function itself. And some people would have taken an additional step on this. Let's do it in 2 lines. I think we don't want to go too crazy, but this is what the additional step would be. Some people might have just wrote the 12 right exactly here after the negative sign because you'd observe it's just going to come down in the next step through this property. So we're going to take this and just throw it down there. So y is now equal to log base 10 x cubed plus log base 10 y squared. Then finally, last step, this will become minus 12 log base 10 of z plus 7. It can't go down any further because the addition in algebra, again, causes problems when it's within the function. So we're stuck at this stage. This is the fully expanded form. Now, again, imagine if you were differentiating this function. I mean, we actually can't. It's x, y's, and z's. There's too many variables. But they were all functions of x everywhere here. That would be a hard function to differentiate. There would be a chain rule because of the logarithm. There'd be a product rule because of the multiplication, a quotient rule because of the division, a new chain rule because of power 12. It's a lot to get through, and it's just not something you can really complete in an exam setting. If you took this additional step, you're just going left to right, doing simple chain rules at most. It becomes a much faster process. So the big takeaway in section 3.7 is this kind of work right here through properties of logarithms becomes very, very vital. Any questions at all, folks, on getting to that expanded expression here? Okay, we'll practice it some more since on the very next problem, that's how we're going to survive it. So that's our part D coming in next. So for part D, I mean, you could solve this problem. It's a pretty long set of pages working through everything very, very carefully. But we're going to treat ourselves to not working that insanely. Instead, we'll do what we did before and just break this up. So on step 1, we write in f of t equals Now in the numerator, I'll take 2 steps on simplifying this, but if you put 7 in front, then you're doing multiple things at once. And that's not a bad thing. That means you've probably dealt with these a lot already. But I'll break it up and start by writing out, this is natural log 8t minus 9 to the 7th power, then minus natural log t minus 11 to the 3rd power. And this right here is our good old property number 6. So property number 6 gives us that minus right there. Next thing we'll do is move down the exponents. That one's property number 7. I like to visualize it this way because it's, I mean, pretty descriptive if you come back to read the notes on what just happened. And that's property number 7. Now observe each time we're just writing f of t, no primes at all because we haven't even begun to touch the calculus. We're just reformatting the function. F of t is now equal to 7 natural log of 8t minus 9. Then over here will be just a minus 3 natural log of t minus 11. And we did it, folks. That's the expansion phase. The next thing we'll do is differentiate. So we'll call this one f prime at t. But we're done with the expansions. Any questions, folks, on getting to this line here? Okay, the downside of all this is we've eliminated a lot of things. There's no longer going to be a quotient rule. There's no longer going to be a massive chain rule involving the natural log and more chain rules inside. But there's still a chain rule here. We have to be careful. This one is not as dangerous, but we'll still treat it like one just for the sake of best practice to help recognize when a chain rule does come into play. On both of these, the natural log is going to be the outer function. The thing that's going inside, that makes sense to call it the inner function, and that's going to be these things. 8t minus 9 for the first logarithm, t minus 11 for the second one. Now we'll just differentiate as normally. First, it's the constant multiple rule. 7 is going to multiply. This is a derivative. What happens with the natural log is you take the 8t minus 9, you throw it into the denominator. Then you're going to multiply by the derivative of that thing, but we know it's just going to go in the numerator regardless. So this is a good time to retune our derivative for chain rule to write it in the specific format that always occurs with the natural logarithm. You're always going to take these quantities, put them down, 8t minus 9 into the denominator, then they'll go into the numerator where you differentiate. If you just put an 8 in that numerator, that's appropriate too. I'll just assume you've differentiated at that step. That's an okay shortcut to take. When you're learning this stuff, it's a good idea to write out in full just to get that additional practice and reinforcement of why things go where they go. So that's the first one handled. Then we just move over and do it all over again. Minus 3. It's going to multiply the derivative of the outer function, which goes like this. Placeholder in the denominator. Chain rule puts a new placeholder in the numerator, differentiated. And always we copy the same function into both of those placeholders. So that's the format to start. Now all we have to do is complete a couple really fast derivatives. On the first one, we have an 8 here when we differentiate. That 8 is going to be multiplied by a 7, so we'll get altogether 56. Divide by 8t minus 9. And on this one's not so bad. We have a minus. Derivative of that whole function is a 1, so it multiplies 3 and just gives us a 3. Divide by t minus 11. And at that stage, our work is complete. The only way you might do additional algebra is if there was a way to factor out a greatest common factor in the denominator, which could then cancel something in the numerator. I think that's going to be pretty rare. And if it does come up in an exam or quiz problem, I'm not too picky about that kind of stuff. But it could be something in WebAssign where they might complain. So if it says your answer is not simplified, it could just be something simple like that going on. But just a reminder, one thing you never have to do is you don't have to add the fractions together. WebAssign will take that as an answer, but it's not necessary for these kinds of problems. The emphasis is just to get to this step. Well, any last questions, folks, or comments on getting through this one? Okay, so let's try this out again. This is what it's going to look like as a WebAssign problem, and there's a couple that look about like that. But if it was an exam question, on an actual quiz or an exam, it's probably going to look more like this. So there'll be a two-part question where you'll have a function, and it'll say, first expand the function fully using the properties of logarithms, and then differentiate your answer in the prior part. The reason I write an exam question like that is, well, it's good to know how to differentiate something like this through properties of logarithms. It's also a massive hint. This is really, really tough to get through unless we took the additional care of expanding that function. So let's start by doing that work again. This one's the worst case scenario, I'd say. There's nothing this hard on an actual WebAssign problem. I wouldn't ask anything this nasty as a real exam problem. Think of this as purely practice. This is a worst case scenario, in other words. But it's always good to know how bad could it ever get in this class, and there it is. First step is we're going to handle the multiplication through property 5. We'll handle the fact there's a division through property 6. And then for any exponents left over, we'll reuse property 7. So those are the 3 suspects you use quite a lot. So here's our start. T of x is going to be equal to, it has a base of 5, so we'll have to write log base 5. The numerator will get x cubed plus log base 5. And let's fix that one while we're at it. It's a 5th root of 7x minus 8. So we can write 7x minus 8 to power 1 over 5, our standard trick. So that plus came from property number 5 of logarithms. Because there's a denominator, we go to minus next and write in log base 5 of x power 5 plus 3 to the power of 4. And that one was due to property 6 down below. We're nearly done. We just need to use property number 7 3 different times to move those exponents down. And I probably won't write the arrows this time since I don't want the notes to get too busy with too many arrows. Let's just go directly at it. Last step is to take and write that from here we have 3. Log base 5 of x. So that simplifies this one. This is just an ordinary constant multiple rule. Over here, a 5th comes down, so plus a 5th. Log base 5 of 7x minus 8. It's still a chain rule, but the complexity of that chain rule is massively reduced the moment you move the 5th down. It's like you eliminated an entire function in the chain rule. Then we'll do it again, or we'll move over here for a negative 4. Log base 5 of x power 5 plus 3. We did it, folks, and just to be specific, here, here, and here is due to property number 7. Any questions at all, folks, to that stage? Okay, after doing all that work, we're ready for the next phase. We have a fully expanded form. This is its most simplified form for doing any kind of differentiation in calculus. So now we're going to differentiate what we've got, whatever it comes out as. There's still some work to do on this thing, but on the first one, all we're using is this formula. Let's recite it since it is a new one. Derivative with respect to x of log base b of x is 1 over x natural logarithm of b. So there we have it, we're ready to go. And this, by the way, I do this a lot on the notes. It's not just for putting a record down on the notes, it's also a kind of best practice. you start to get lots of formulas like we have in chapter 3, if you write down that formula the moment you're about to use it, it's a great way to retain that formula as well. Even if it's posted on the notes, the more you memorize about it, the easier it becomes to work with the formula. So I encourage you, write them down a lot. Before you know it, you will be forced to memorize it. You just can't help it at a certain point. So that's our key formula. We'll use it right here and start by saying, now t prime at x, we're dealing with the derivative now, becomes 3 stays right where it is in a numerator. Derivative of a base 5 logarithm, we'll put x down below, multiplying the natural log of 5. That's the natural log b part, where b is 5 in this problem. That's not a bad thing to write. B is 5 for our problem. So that takes care of the first one. The next one is trickier because it's a chain rule, but it's not too bad as far as these go. Chain rules for logarithms always kind of go the same sort of way. For this one by the red dot, we'll start with a constant 1/5. Then the process is, take that and drop it to the denominator. We'll need a parenthesis because it's also multiplied by the natural logarithm of 5. We'll see this natural log 5 on all the denominators. Then once it went to that denominator, it goes up above where it will be differentiated. I'll take an additional step to show that, but if you just put a 7 up there, good call. That's pretty much all that happens. If you take that shortcut, I'll assume that you've done this a lot, and that's the right shortcut to take. Then let's just do it all over again. This will be -4 times a new fraction. Throw that down to the denominator, x power 5 plus 3. The base we identified as 5, so we also multiply by that. Which means an easy way to lose points in a simple mistake is, don't forget the parentheses. WebAssign will complain about it, and you could lose like a single point. I wouldn't fuss as much as WebAssign, but they are required for correctness. Then in the numerator, because it's also a chain rule, we'll go x power 5 plus 3 prime. Any questions, folks, to that stage? Okay, that's a lot of stuff, but what you want to do is just focus on one thing at a time. Do the derivative methodically, step by step. And what you're really visualizing is, it's just 3 natural logarithm or logarithm problems that you're doing all at once, kind of duct taped together by pluses and minuses. So now to finalize this, we just need to do 2 more derivatives and simplify. So first term is already done. 3 over x natural log 5. Plus, on this numerator, we have a 7. For the denominator, I'm just going to combine all 3 factors. 5, 7x minus 8, and natural log 5. So that takes care of the second fraction. On this one, let's do a couple things at once. First, I'm going to leave the negative right where it is. And we know the derivative of x power 5 plus 3 is going to turn into 5x power 4. But then the -4 is going to multiply that. And so we get altogether -20 x power 4 in the numerator. And down below, we're just copying now. X power 5 plus 3 times the natural log of 5. Now that I've done that, I notice I've also made a mistake. I was looking at that -4. I multiplied by the 5 the result of that derivative, and I wrote at -20. Seemed right, but I already had the negative there. That should have been a positive sign right here. If I move the negative into that position, I would have to go positive there. Does that weird mistake there make sense to folks? Awesome. That's a weird one because it's a mistake where you correct it by deleting it, but it was there. Don't do as I did. That should be a positive with a negative right there. Other questions, folks, on getting through this one? Okay, so I would consider this to be the worst case for the derivatives. I don't think there's anything this bad on WebAssign. But if you felt like, well, we can get through it, we just have to be slow and methodical, then that's kind of the experience in section 3.7. The problem above, this one is a typical problem like you'll see. That's the same strategy that we just used applies to several WebAssign problems as well. Well, we got through a lot. Let's see what we have going on next. Aside from doing all these kinds of derivatives, there's one additional formula that doesn't seem very impactful right now, but in chapter 4 and chapter 5, it does become a big deal. It's this formula right here. It's a curious little formula. It says, let me hide this just down below in case we need it. It says if you're differentiating the absolute value of the natural log of x, you still get 1 over x, despite the fact that there's an absolute value. Now, before we take a look at this formula a little bit more, we should visualize it. So let's go to Desmos real quick. Because one question you might have, I know I had this question myself, is why is there suddenly an absolute value here? We didn't worry about absolute values a lot in this course, but suddenly we have to deal with it. Here's one reason. If you write y equals natural log x, observe that the domain is pretty restrictive in a certain sense. And in chapters 4 and 5, we're going to start undoing differentiation. This is going to be considered the question, and that's going to be considered the answer. The reason the absolute value is important is this domain is pretty small in a certain sense. If this is the function you're focusing on, if it's the question, like in chapters 4 and 5 coming up, the domain of 1 over x is all real numbers except 0. So we want to have the answer have the same feature, domain all real numbers except 0. In other words, we want the part of the curve to show up here as well. We could do that by just throwing in absolute value of x. But maybe, let me try again. Natural log, absolute value of x, there it goes. Now, the moment you throw in absolute value, the domain on the left-hand side matches the domain on the right-hand side. All real numbers excluding 0. So that's one of the reasons why we want the absolute value there. But it's still kind of a tricky formula. Somehow, some way, when you differentiate this thing, absolute values come off, and that's super surprising. So I'd say, before we do example 3, let's actually do this derivative and show how it should go. Any questions at all, folks, before we start? Okay, so if we're going to differentiate this one from scratch, the first thing we need is the definition for absolute value of x. And there's a lot of definitions. You could say it's the directed distance from 0 on the number line, but that doesn't help us too much here. What we need is the definition of absolute value as a piecewise function. As a piecewise function, the absolute value of x is x. Then we put in a comma to say what domain that's relative to. Absolute value of x turns into x, provided that x is bigger than 0. We can say bigger than or equal to 0, but I'm writing down, well, let's just say it that way specifically. I'm going to have to eventually take off equality at 0 because natural log is not defined there, but this function is. So let's put in the full definition. Now, if you put in, say, absolute value of -3, what really happens algebraically is you take the negative of -3, and it comes out as a +3. The absolute value of that quantity cannot be negative. Algebraically up here, this is what it looks like. Absolute value of x is -x, provided x is negative. There's really 2 negatives right here, and it forces a positive quantity in that location. So that's the first thing we have to do. And then beyond that, in order to derive this formula, we need to work with the piecewise function directly. So y becomes, well, it's natural log of absolute value of x, but it's actually a piecewise function truly. It breaks up like this. Try again on the curly brace. There we go. It'll turn into natural log of ordinary x if x is positive. Here I have to put directly x greater than 0 because we can't put 0 inside a logarithm. It would be undefined. Now, next thing we'll say is, well, over here, if there's a negative x, we'll put down here natural log negative x, and this is provided x is negative. That makes sense because if x is negative here, there's really 2 negations, and you can calculate that natural logarithm. So that's our first step. Next step, we're just going to differentiate all of this that we see here. It will go like this. dy dx. I believe this is the first time we've differentiated a piecewise function, but it's not so bad. All you do is you focus on one piece at a time. We'll first differentiate that first piece. So if we differentiate natural log x, that's our nice formula. It just turns into 1 over x. Nothing else exciting happens. And this is provided that x is bigger than 0. That's this portion of the formula here. We're getting 1 over x, but we still haven't explained why should we get 1 over x when we differentiate that line. That's where all the contention and confusion is in this kind of problem. It's kind of a surprise. Because it's confusing enough in its own right, let's do it over here. Let's say we have some other function, y equals natural log negative x. On face value, that doesn't even look like it's defined unless you say x is negative, so you truly are throwing positive values inside. We want to differentiate this to complete our whole derivation, but it's now a chain rule. Natural log is the outer function. Negative x right here, that's the inner function. So let's work this one out carefully. Y prime is going to go like this. Each time we differentiate, we'll take whatever is there, drop it down into the denominator. So there it goes. In the numerator, you take the same quantity, but you differentiate it. So it goes like this. And to me, this is when it finally becomes clear. Sure, there's a negative x down below, but the derivative of that numerator is a negative 1. The negatives cancel and turn into a 1 over x. And that's the whole reason why this, if you differentiate it, because of the chain rule and only because of the chain rule, you get 1 over x. And this works when x is negative. That tells us this really is the right formula. Differentiate the absolute value of x. It's a piecewise function, sure, but that piecewise function simplifies finally to 1 over x after we show both pieces are the same on those opposite domains. So this is the formula. Everything else is, well, practicing with chain rules, piecewise functions to show why that formula really is correct. For a lot of people, when you stare at that, it looks like there's a literal typo, like absolute value is missing, but it's not. That's the right formula in its most simplified form. Well, any questions, folks, with that one there? Okay, well, armed with this knowledge, finally, let's handle that derivative. Let's copy the formula that's now suddenly invisible. Derivative with respect to x, absolute value of x, and that's not quite what I wanted. Let me try again. Derivative with respect to x of the natural log of the absolute value of x is simply 1 over x. So with that in mind, here's our new formula. It's another chain rule, but they honestly go pretty nicely each and every time. You might notice that we're going to start writing out outer and inner function when we see these logarithms. Let's just directly go at dy dx. There's an absolute value on this thing, but what our formulas say is that's irrelevant. It'll become relevant in chapter 4 when we need that, but for the moment, when we differentiate, we drop absolute value, put in x cubed plus 4x squared minus 1. Then into the numerator, same thing, but differentiated. X cubed plus 4x squared minus 1. If you put in 3x squared plus 8x, that's the right step to take, I'd say, but we're showing extra steps just for the notes to show a paper trail of how we get there. So derivative on the numerator is 3x squared plus 8x, and the constant here vanishes. Down below, x cubed plus 4x squared minus 1. So we did it, folks. That's our derivative using our fancy new formula over here, which essentially says you are free to ignore absolute values. That's wonderful when you can ignore stuff. All we now need to do is evaluate the derivative. We'll get the slope of the tangent line on the graph right where x is 2. So this one is just a quick function evaluation, dy dx, evaluated when x is 2 just means Plug 2 everywhere x occurred. This will be 3 times 2 squared plus 8 times 2. Then down in the denominator, nothing too fancy, it'll be 2 cubed plus 4 times 2 squared reduced by 1. If this was an exam question, my expectation is you're probably just putting that into a calculator, which would be appropriate. But let's see if we can work it out. This is good practice as well. That's 4 by 3, so a 12. Oh, and I lost my red dot. Let me bring that back. We have a 12 from this location. 8 by 2 is 16. Down below, this is 8 plus 2 squared is 4 times 4 for a 16. And then minus 1. It honestly does feel silly doing this kind of stuff in a calculus class. But I promise you, working this out by hand, it's good practice because it's not just arithmetic. It's reminding you how algebra works as well. The more you get fluent with this, the more the algebra you see in this course becomes a little bit easier to navigate. So if you have the time to just crank it out by hand, it is worth the effort, in my opinion. Numerator is now 28. The denominator is 24 reduced by 1. That's a prime number, so it tells us it's simplified right at that form. So that's how example 3 goes on these notes. And I think, folks, we've actually ran out of material. These are the kinds of problems that you're going to see in WebAssign. I didn't have anything much more beyond this one. Any other questions or comments, folks, on getting through these logarithms? Okay, well, I didn't intend to, but we actually finished this one early. So when we come back after the break, we'll finally be in chapter 4. We'll look at some quick applications of the derivative. And then the major thing in chapter 4 is we're going to start working backwards. What I mean by that is, kind of like we said before, this line is going to be the question, and the original function at top is going to be the answer. We need to now invert all of our differentiation formulas, and we'll start calling them antiderivatives. Honestly, it's a good opportunity to just practice differentiation even more. There's never enough practice you can get in on these things. But we're going into spring break, so I hope you don't work too hard. If you do have any questions, I am available by email. I usually check early in the early morning. But even if you're emailing me at 5 p.m. or 3 a.m., just write that email, and I'll see it the moment you had that question when I check it in the morning. Well, any last questions at all, folks, before we go off to the break? Okay, well, have a great break, folks, and I'll see you all in a couple of weeks or so.